Okay. Alright, Assalamualaikum warahmatullahi wabarakatuh and good morning. So for today lab session, we are going to do lab 3, but I'm going to ask you to open the lab 2 because that's where part of chapter 3 is included, okay, for the questions. So you download lab 2 first, okay, so then here, the two's complement, So I did teach you about the two's complement, right? So now for the exercise, okay. So here they have the notes, for the two's complement for binary and also two's complement for, oh, there's no two's complement for the B16, right? So for the B16, we refer to the lecture notes, So, now go to the question 9 and 10. Okay, so the instructions that I have given you for lab 3 is that if you open your lab 3 S2G2, you need to answer the question for question 9 and 10 in lab 2. So I'll teach you a little bit about question 9 and 2 for you to answer, 9 and 10 for you to answer. And then all the questions in lab 3. So this is all the exercises that I want you to do. So now for questions 9, does the addition of following 4-bit 2's complement numbers generate an overflow? So you need to justify your answer. Okay, so so I need to remember my questions, and then at the same time, I need to let me make it smaller, so that I can still see it in my screen. Okay, just a little bit for the size. Okay, so I hope you can see this. All right. Now, the question is a 0111 and a plus 1001. So the first thing first that you need to remember is that they said that the question says it's a 4-bit 2's complement. Okay, so if it's a 4-bit 2's complements, okay, it means that the first one or the most significant bit here is a sign bit, and then the rest 3 bits here is the magnitude. We call it magnitude. Okay, so we call these 3 bits as a magnitude and this one as the sign bit. Okay, why do we call it as a sign bit? You need to refer back again to the previous notes. Okay, on this part here, look at this 2's complement. Okay, as I have mentioned in the lectures, the most significant bit is to tell you the sign bit. If it's a 0, means it's a positive. And if it's a negative, we represent it by 1. In a binary, they don't consider negative as a sign bit. Okay, they use binary numbers. Okay, so now for this 2's complement, okay, when we want to represent it using a 2's complement, so we need to use the first complement first. Look at this step. Each 0 is changed to a 1, and then each 1 is changed to a 0. And then to convert it to 2's complement, we add 1 to the first complement, the one that we have previously calculate or convert it, okay, to become a 2's complement. So that's the step for a 2's complement. In actual case, usually we ask the student to do a 8-bit 2's complement compared to 4-bit 2's complement. But this is just to show you what does it mean overflow. Okay, so first thing first, you need to remember about sign and magnitude. Second, now we do the operation. Okay, so when you do this operation, okay, 0, 1, 1, 1, 1, and then 1, 0, 0, 1, right? So 0, 1, 1, 1, and then 1, 0, 0, 0. You need to add it together. Okay, so you need to remember this one, the second number is a 2's complement because this is a sign bit of a negative. Okay, so I'll just need to add it as usual. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. And then 1 plus 1, 0 plus 1 is 1. Okay, my mistake. Sorry. It's supposed to be 1001, right? Okay. If I mistakenly do this calculation and then you check that it is wrong, please remind me, okay? So 1 plus 1 is 2. 1 plus 1 is 2. And then 1 plus 1 is 2 also. This is 1 plus 1 is also 2. Something wrong. Did I make a mistake? 1, 1, 1, 1. 1 plus 1 is 2. 1 plus 1 is 2. 1 plus 1 is 2. So, okay, betul. So, 1 plus 1 is 2 also. So, when we carry forward, 1 is 1 here. Now, if there is an extra bit, because this is a 4-bit 2's complement, right? So, we only need 4 bits. Then, this last one here, okay, the most significant bit or the extra bit here would be drop. So you write it drop. So the final answer should be 0, 0, 0, 0 base 2. Now you need to check. You need to check if it's overflow or not. So to check that it is overflow or not, you need to calculate it using a decimal first. So you convert this the first number to a decimal, second number also to a decimal. So this is a straightforward because this is a positive number. So positive 7, right? But now this one is 1001, which is 2's complement. So you need to convert it first. So 1001, convert it to a 1's complement. So now it will become 0, 1, 1, 0 plus 1. Then you will get 1, 1, 1, 0. So if it's a 0, 1, 1, 1, then this is a case of can I move it? Oh, dah habis. Alright. So 0, 1, 1, 1, 1, 0, 1, 1, 1, it's a positive 7. So means that 1001, if we reverse back again the process, so this is actually a negative 7. So 7 plus negative 7, you will get a positive 0. Okay, means that it's a 0 lah. It's a 0. So does it reflect 0, 0, 0, 0 here? Does it reflect to the decimal here? Yes. This is a 0. Then this is your final answer. So means that is there any overflow? No. Okay, it's not overflow. Okay, now why is that? It's because of what we have here. The sign bit here is actually a sign bit itself. So there's no value. So there's no value. So what does it mean? Overflow is that overflow is when you do some addition or subtraction, and then it exceeds the value or the magnitude. The magnitude should be in 3 bits, right? So now, when we do some calculation like this, 1 plus 1, and then it is 2, and then there's an extra bit that it needs to carry out. Okay, you need to carry out to the next bit. So if there is an extra bit there that that should be a magnitude itself. So when the sign bit become a magnitude, okay, which is supposed to be a sign bit itself. Okay, so the position should be a sign, but then was replaced by the magnitude, then that's overflow. That is an overflow. All right. So your justification is that since the most significant bit is a sign bit of a positive number, then it is not an overflow. Okay. Now let me continue with the second questions. 1001 plus 1111. Okay. So I'll go down. Now we follow the same thing. This is a 4 bits. Now I need to calculate 1001 and then plus 1111. I would plus it together and then I would add it as usual. So I know this is a 2's complement of a negative number. Okay, so negative number plus negative number. So is there a possibility of an overflow? Okay, so we will see it later on. So 1 plus 1 is 2. So 0, 1. And then 1 plus 1 is also 2. 1 again, carry forward. 1 plus 1 is 2 again. Carry forward. Now this is 1 plus 1 plus 1. 3. Now this becomes 3, then 1. Carry forward 1. And then we place this extra bit. Now we have 5 bits, right? We have 5 bits. And now this one, we need to drop it because the size of the 2's complement is a 4 bits. Okay, so we drop this. Now what about this? The answer is 1000. Okay, so 1000. So here means that the answer should be 1000 base 2. So you just need to know, is this an overflow or not? Okay, so if it's an overflow, you need to check. Okay, so 1001 is previously we have done this, right? 1001. Go back to the top. It's a negative 7, huh? So this 1001 is a negative 7. So 1111, we need to convert it. So 1111. We need to know what is the actual value of these 2's complement. So 0000 as a 1's complement, then plus 1. Then you will get 1000. So this is a 2's complement, okay, for a positive 1. So if we reverse back again, then you should get this is a negative 1. So you will write this as a negative 1. Now what would you get is that negative 7 plus negative 1. So the final answer should be negative 8, right? So the final answer, it should be a negative 8. But what would you have here is that 8, okay? And here is like a 1000, but this is not a negative 8. So what we have so far is not negative 8 because you need to convert back again. Okay, what is the actual negative 8 in 2's complement? So you know that 8 is 1000, right? Okay, and then because this is not a sign, this is an actual value, so you must have extra bits, which is 4, okay, to represent that this is a positive 8. This is a positive 8. Now to tell that, okay, this most significant bit here, okay, 0, and then a string of 0 here to represent that this is a positive 8. Now, we use the first complement to convert it to a negative. So now it will become 1, 1, 1, 1, and then 0, 1, 1, 1. And then we plus 1. Now you would get 0, 1 plus 1 is 2, 1 plus 1 is 2 again, 1, 1, 1, 1, 1. Now, this is exactly of a negative 8 in a 2's complement. Okay, so why is that? I said that we need to use an extra bit. It's because of we need to have an extra bit or the most significant bit to be assigned bit. So this fourth bit here, 1, 2, 3, 4, here, this one, the one that I have underlined, okay, it's an actual value. So I want to ask you again, if we convert it to the 2's complement, is this a magnitude or a value, or is it a sign bit? This is a question I want to ask you. You unmute yourself, you tell me, is this the one that I have underlined for the negative 8? Is this a sign bit or a magnitude? No one wants to answer the question?
A magnitude.
Magnitude. Okay, correct. So because once you have done this calculation, you know that at the moment, from the positive, okay, this one bit is actually a magnitude, so it would carry down. Okay, it is exactly the same as a magnitude itself. So in this case, this one, when you want to convert it back again, and then what you have here, so you need to mention this one is not a sign bit. Okay, this is not a sign bit. You scratch it, and then you write, it has become a magnitude. So in any case, this is an overflow. So do we need to produce this answer? 1002? No. You cannot use this as an actual answer. You just need to write it is an overflow. Okay, you write this as an overflow because this bit has changed from a sign to become a magnitude. Okay, so that's how you need to answer. You need to follow the size of the 2's complements number. It's also the same for the question 10. Question 10, following 8 bits of 2's complement, you generate, does it generate an overflow? So you need to check, okay? When you do the 2's complement, you need to make sure the size of the bits must be the same. This one is 6-bit, 100001, and then plus with 1111011111. So it's an uneven size, right? So you need to make sure, okay, you need to make sure it is the same size. So it must be in an 8-bit also. Okay, and then as for this one, okay, this one is 1010011. And then plus with 11110000. So add it together, okay, and then look at it if it's generating an overflow or not. Okay, the key is that if the sign becomes a magnitude or not, then that's your answer. Okay, so that is for question 9 and 10. Okay, now let's look back on the lab 4, lab 3, Lab 3, okay, okay, week 3. Now, for the week 3, this is the lab 3 questions. You open it. So this is notes for the lab 3 questions. So I do have my own. So I just need to I just want to use this window. It is easier for me. And now this is the all questions that you need to answer. Okay. I'll make it a little bit. This one. Okay. Now you need to perform. Don't follow this one. Okay. It's because of I just want to use this. Okay. Now perform the following binary numbers addition. Okay. So I would suggest also you use same size. So if the second number is an 8-bit, then the first number must be an 8-bit also to make it easier for you to do the arranging the questions. And then also the same for the other questions. Okay, I would like you to do these fraction numbers as your exercise. Okay, so please expect that it will be much more bigger numbers if you are using an extra a fraction numbers. So you can do that exercise later on, but only for this lab session you can do all these questions. Okay, and then perform the subtraction. For the question 2, this one, it's a normal subtraction. Okay, it's a normal subtraction. So in this case, for question E there, okay, for question E, yeah, hold on. So for question E, there's a cases of a negative number, right? That's a cases of a negative number. The previous group, I asked them to do something like this: 11.010 base 2. Okay, and then 111.01. So you just subtract it as usual. Okay, you just subtract it as usual. So you just negative 8 like that, and then you just subtract it. So 0, 0, 0. Okay, and then 1 minus 1 is 0, 1 minus 1 is 0. Now, we don't have any value here because this is a 0. So we imagine that there's an extra bit here. You need to borrow. Okay, this one become a 0. Then this one become a 2. 2 minus 1 is 1. Okay, but then you need to, because we borrow it somewhere that doesn't exist. So what do we need to do? You just put a negative. Although this is not a I told you before, right? For negative number, it cannot be used to represent a negative cannot be represented in a binary. But in this case, you may write like this. The negative also can. But if you want to write it like this, negative in the front, also can. Because this is like a number subtraction, like a normal way that you do when you do like a decimal. Okay? And then now, for multiply and hexadecimal numbers, so I want you to do all these questions. Yes. Okay, so please take note. Question F. 11 base 2 times 11 base 2. Okay, so please don't question me again because I already mentioned it. Okay, so you write the notes. Okay, question 3F is actually 11 base 2, 1 base 2 times 1 base 2. Okay, so I'll give you time to write this question first for question 3F so that you will remember. The next time I will find out someone asked me this question again, I will mark you down, because I know that you are not listening to me. Okay, next, divide the following binary and hexadecimal number. So as I told you before, okay, we do this. Follow the notes in the lecture. Follow the notes in the lecture. Okay, so for question 4A, 1010 base 2, and then divide by 111. Okay, can you see that there's something missing? There's a base number that is not mentioned after 111. So just put 2 there. It's a binary number. So 1010 base 2 divide by 111. Okay, next. For question B and question F, there's a small number divided by bigger number, right? So, usually, if it's a normal decimal, okay, like this, okay, 1 divided by 1 we know that this size is bigger than this one. So in actual fact, we just get 0, and then 0 is actually 1. So your answer can be 0 base 2 remainder, something like that, 1 base 2 also can. But what I want you to do is that you do two style of answer. Okay, one is that you answer it like this. 1 divided by 110. Okay, this is a 0. You borrow bit. How do I say? Yes. You add an extra bit, and then at the top, okay, the answer, okay, for the division, okay, for the division answers, then you put a dot there. So, and then you add a 0. So in this case, when we add a 0 here, so 110, okay, this is a 0, and then what we get is 1, and then we put it down 0 lah. Okay, 110 divided by 110. What will you get? 1. So 1 times 110 is 110. Okay, so 110 dot. So your final answer is 0.1 base 2. Okay, now you do these two styles in your notes, in your exercise. Okay, so that, let's say this one need to be continued. Sometimes this will be continued until how many decimal places, or how many points do we need to continue to do this division. So in actual, let's say that's happened later on, you can stop after 4 decimal places. 1, 2, 3, 4, or 5. Okay, let's say 5. And then if there is still remainder, then you stop. You stop it. Okay, you stop. Okay, so indeed, in that case, if there is a remainder here, so you will write 0.1 something remainder. Okay, so but you don't need to put the remainder anymore actually, because this is actually, point here is actually a remainder. So you don't have to mention it lah. Okay, you just put the 0 point something. Like that. Okay. Now, before I want F7, then FB16. Okay, next is question 5. Sorry. Question 4 and 5 is the same thing, but the difference is that, sorry, it's not. It's different. One is a division. Question 5 is 2's complement. Okay, so 2's complement. Sorry, let me add previously for the division. Let's say for the hexadecimal, this is too big, right? And then you don't want to do the multiplication table for 10F. Let's say you don't want to do that. So what can you do? Remember that hexadecimal can be represented into binary. So you convert these numbers to a binary, and then you divide it. After that, you change it. Okay, you convert it back to hexadecimal. So let's say in this case, there is this is a normal one, big number divided by small number. Then I would suggest you don't need to put the remainder anymore. You just take out the division only, the division result. Okay, so only the division result that needs to be converted to hexadecimal. Okay, but if you want to continue with the 4 decimal places and then convert it like this, this one. Okay, let's say, mana pen aku ni? Ke sini. So let's say your answer is 1110 dot something, 0, 1. Okay, 00 base 2. Then this is the final answer, and then you need to convert it to hexadecimal. Okay, so when you convert it to hexadecimal, then this should be E dot 4 base 2. So that's it. You can also do that. Okay. So that is for question 4. For question 5, question 5A is a decimal. So first is that you need to convert it to 2's complement. Binary number first, and then if it needs to be converted into 2's complement, then you convert it. So you might want to be thinking, 2's complement is for positive numbers, for negative numbers, right? So in this case, you just convert it to a positive number. So in this case, let's say this is 17, yeah? So 17 is 0, 0, 0, 1, 0, 0, 0, 1, just like that. So this is a positive 17. So do I need to convert it to 1's complement plus 1? No. It's because of the questions only asked to add positive 17. Positive 17, right? So no need to change it to 2's complement. Okay? And also with the 83. Okay, question B, 119 minus 13. Now, this is where you see a subtract, right? So then, negative 13. So now we will do the operation 119 plus negative 13. So negative 13 here needs to be converted to 2's complement. Okay. So what about question C? Negative 15 plus 20. Then negative 15 must be converted to 2's complement. 20, you just convert it to positive 1. Positive binary numbers. Okay. Now, question D, E, and D and E is the same thing. F also is the same thing, eh? Now, for these questions, 7, also the same. Let me check. Yes, that's it. Okay, it's the same thing. You can do this operation lah for the subtraction using the 2's complement. So for these questions, okay, regardless of the size, okay, try 8-bit 2's complement first. 8-bit 2's complement lah, except for the hexadecimal number. Hexadecimal number depends on the size of the numbers of the hexadecimal. So in this case, this one is 4 bits, right? 4 hexadecimal numbers. So 4 times 4 is 16 bits in binary numbers, right? So let's say you have that question like this. Then you follow the notes that I have teach you, okay, for that questions. Okay, so now for question 6. Let me delete first. Okay, now here ASCII code, it's a standard that is used to convert, okay, the keyboard in front of you. Okay, so how does the computer recognize that you are pressing D or you are pressing H? It's because of these codes here, the ASCII code. So every time when I press this, it will be converted into an ASCII code. Then it will be processed in the CPU. Okay, so to do some operations such as to display it back again, okay, based on the one that you have pressed down using the keyboard. So there's a lot of things of translation or encoding of what you call inside the computer. So now let's say you want to represent, okay, you want to display the message of pay RM100 that is input from the keyboard. Okay, so the message is started from the PAY. Okay, start from P. So means that the inverted or the code is ignored because that's a symbol to indicate. If it's open code, means that the message start here. And then if the close code after that, means that the message and here. So in this case, what you recognize as the message is PAY space RM 100.00. So let me use this part. And then close quote again. Okay, close inverted comma. So what you need to consider? Only this part. Okay, now how do I need to convert it? You refer to the ASCII table. So first is that each of these character is represented by one ASCII code. So you just need to read the ASCII table and look at the certain characters. Okay, for capital letters and small letters, they have a different ASCII code. This is an incomplete of ASCII code. You can just Google and then they would display all characters that is available for your on your keyboard. So but because of the spacing problem, so we just these notes only represent the capital letters and special characters. Okay, now look at the character P on the ASCII table. So the ASCII code for P is 1010000, and then A is 1000001, and then Y, and then there's a space here. Okay, there's a space from the keyboard, right? So you write space. So what is a space? 010 010, and then 0000. Okay, and then there's a RM 100 ringgit. Okay, so dot is represented by this dot 010 Okay, so once you have finished this finding out the character, then it's time you combine all together. So the entire message of this pay RM space RM 100 ringgit is that 1010000, continue 1000001, and then you continue to produce a string of lines, a string of binary numbers. Okay, so that's it for question 6. Now, that's all. I would give you times, okay, and then I would mute myself only that you have a questions. You unmute yourself and then you tell me, okay, tell me what the questions and what you don't understand, okay? So if you want to leave now, yes, you can, but okay, I have mentioned the lab notes, the lab assessment must be completed before Wednesday next week, before actually midnight Tuesday. Okay, so you do all these exercises when you have free times. Actually, at this time, you do what you can for the ones that you are not sure. So I will be available here. Okay, if you have a questions. Okay, so that's all.
Madam.
Ya, ya, siapa? Siapa tu?
Saya, Aiman.
Ha?
Aiman.
Iman. Tak ada nampak pun nama tak unmute-nya. Mananya korang ni? Oh, okay, okay, okay. Ha, nampak, nampak, nampak. Uh-huh.
So, Madam, yang soalan 6 tu kan kita kena tulis setiap huruf tu dia ada dia punya nombor binary tu kan.
Betul.
So kalau dah habis sampai 100.00.00 tu pun kena tulis juga kan setiap satu tu.
Betul, betul.
So and then dah tulis semua tu baru campur balik.
Betul.
Kena tulis balik bawah tambah semua nilai tu.
Ya,
Setiap
kena
binary.
tambah semua nilai tu. Dia nanti dekat dalam communication tu dia combine all these notes lah to tell that this is the content of the message. Message tu
Oh.
memang ada lah, tapi dia ada extra proses selepas tu, selepas there's an extra process after we convert it to an ASCII code. To combine all this to become a whole message, then they need to do some padding, they need to do some start bit and stop bit, but that one you ignore it first. Because there's a lot of subject that will cover that part. Okay, you will learn about that part, but this is only between the communication or the transition between the peripheral, such as like a keyboard, to the CPU. This is what happened when you press P. When you press P, what the computer will recognize is this 1001. Let me share back again. Okay. Now, what it recognizes is this number, not P itself. The computer only understands binary numbers. So, like I said before, they only recognize a binary. So, we need to make the computer understand about this character, right? So, that's why they use the ASCII code. So, you just combine it together. So, when you combine this, it will become like a string of numbers that tells a message. That was telling you a message about it. So when the computer convert it back again to the output, like on the monitor, it should change back to this one should be P, this one should be A, this one should be Y, and then there's a space, and then the next. So even the space and the dot is very important. It's very important. So
Yeah.
like when you are trying to write on your C++, so to represent the floating numbers, they require the dot. Okay, so they require the dot. So in actual fact, the dot is not exist in the binary number itself. But then they have to convert it, okay, to make sure these numbers can be covered up. So they come up with this ASCII. So this is a number conversion also actually. It's actually a conversion number. If you look at the question lab 2, okay, there's a lot of conversion numbers like a BCD, non-weighted binary codes. This one is not that popular. ASCII is much more popular. It's because of its the standard. Okay, the standard that is used all over the manufacturer. Because who doesn't use the keyboard? That's what I'm saying. Okay, so they use the same standard. So to make it easier for the CPU to convert it. Okay? Boleh?
Okay. Boleh, madam. Thank you.